Today we are going to learn about mastering grid search for hyperparameter optimization. In this session, we will explore how to effectively set up, execute, and interpret grid search to enhance the performance of machine learning models. Welcome to our session on mastering grid search for hyperparameter optimization. In machine learning, hyperparameters are crucial settings that influence the performance of a model. Unlike model parameters, hyperparameters are not learned from the data but must be set before training. Grid search is a methodical way of tuning these hyperparameters to find the best combination that enhances model performance. We'll explore how grid search can systematically test various combinations of hyperparameters to identify the optimal settings for your model. We'll also highlight how Scikit-learn, a popular Python library, facilitates this process with its user-friendly tools. Understanding how to effectively use grid search is essential for improving your machine learning model's accuracy and efficiency.
To begin using grid search, we first need to set up our environment. We'll be using Scikit-learn, a powerful machine learning library in Python. Start by ensuring that Scikit-learn is installed in your environment. You can do this via pip with the command pip install Scikit-learn. Once installed, import the necessary libraries, including the model you wish to optimize, such as a decision tree or support vector machine, and grid search, the tool used for performing grid search. Define your model with initial settings, then create a parameter grid. This grid is essentially a dictionary where keys are the hyperparameter names and values or lists of settings you want to try. For instance, if using a decision tree, you might include max_depth and min_samples_split as keys. Finally, initialize grid search with your model, parameter grid, and other settings like the number of cross-validation folds. This setup prepares you to execute the grid search process. Selecting the right parameters is crucial for effective grid search. Begin by identifying hyperparameters that significantly influence your model's performance. For example, in decision trees, max_depth and min_samples_split are key. It's important to balance complexity and model performance. Too many parameters can lead to overfitting, while too few might not capture the model's potential. Research common parameters used in models similar to yours, and use these as a starting point. When setting ranges for parameters, consider a broad range initially, then refine based on early results. For instance, you might start with max_depth ranging from 1 to 10 and later narrow it down to 3 to 7. This iterative refinement helps in focusing the search and reducing computational costs. Remember, the goal is not just to find any solution, but the best one that generalizes well to unseen data. Grid search, while powerful, can be computationally expensive, especially with large parameter grids. Understanding this cost is vital. There is always a trade-off between the thoroughness of the search and the resources available, both in terms of time and computational power. To manage this, start by using a smaller dataset to test your grid. This provides quick insights into which parameters are more promising. Additionally, consider reducing the search space by focusing on the most impactful parameters or by using a coarser grid initially. Once you identify promising regions, refine the grid for a more detailed search. Another effective strategy is to parallelize the grid search process. Scikit-learn's grid search supports parallel execution, allowing you to utilize multiple CPU cores to speed up the search. By balancing these factors, you can efficiently explore the parameter space without excessive resource consumption.
After executing grid search, interpreting the results is the next crucial step. Grid search outputs a wealth of information, including the best parameters found, the best score, and detailed cross-validation results. The best_params_ attribute provides the optimal hyperparameter values, while best_score_ gives the highest cross-validation score achieved. Evaluate these best parameters by retraining your model with them and comparing its performance to baseline models. Additionally, examine the cross-validation scores for each parameter combination. This helps in understanding the model's stability and generalization capability. Visualizing these results can provide further insights. Use plots to display the impact of different hyperparameter values on performance. This not only aids in understanding the results but also in communicating findings to others. By carefully analyzing grid search outputs, you can make informed decisions to enhance your model's performance. Overfitting is a common issue during hyperparameter tuning, where a model performs well on training data but poorly on unseen data. Recognizing signs of overfitting, such as a high training accuracy but low test accuracy, is crucial. The key is balancing bias and variance. Too much bias leads to underfitting, while too much variance causes overfitting. Employ strategies like using simpler models or incorporating regularization techniques. Regularization, such as L1 or L2, adds a penalty for larger coefficients, discouraging overly complex models. Moreover, ensure robust cross-validation, which helps in assessing the model's ability to generalize. Using k-fold cross-validation, where the dataset is split into k-parts, ensures that the model is trained and validated on different subsets of data, reducing the risk of overfitting. By understanding and addressing overfitting, you can develop models that perform well on both training and unseen data.
Let's apply our knowledge of grid search to a real-world dataset. We'll use the popular iris dataset, a well-known dataset in machine learning, which classifies iris flowers into 3 species based on 4 features. Our goal is to optimize a support vector machine, SVM, model. We start by defining the model and creating a parameter grid. Key parameters for SVM include C, the regularization parameter, and gamma, the kernel coefficient. We set a range of values for these parameters, such as C ranging from 0.1 to 10 and gamma from 0.01 to 1. With our setup complete, we execute grid search using grid search. Once the search is complete, analyze the best parameters and scores. In our case, this might reveal that a C of 1 and gamma of 0.1 provide the best performance. Finally, retrain the SVM with these parameters and evaluate its performance on a test set. This case study demonstrates the practical application of grid search in optimizing machine learning models. Improving grid search efficiency is crucial, especially when dealing with large datasets or complex models. One alternative to grid search is randomized search, which samples a fixed number of parameter settings from specified distributions. This can often yield good results with less computational cost. Implementing early stopping criteria can also enhance efficiency. If a model's performance doesn't improve significantly after several iterations, it's better to stop and reassess the approach. Focus on prioritizing parameters that have the most significant impact on performance, and leverage domain knowledge to guide your choices. Understanding the data and the context of the problem can provide invaluable insights into which parameters are likely to be most effective. Lastly, adopt a mindset of continuous learning and adaptation. The field of machine learning is rapidly evolving, and staying updated with the latest techniques and tools can provide new ways to improve grid search efficiency. By incorporating these strategies, you can make the hyperparameter tuning process more effective and less resource intensive. In conclusion, mastering grid search for hyperparameter optimization is a valuable skill in the machine learning toolkit. We've covered the setup and execution of grid search using Scikit-learn, choosing the right parameters, balancing computational cost, interpreting results, and handling overfitting. The practical application of these concepts, as demonstrated in our case study, highlights the importance of methodical hyperparameter optimization in enhancing model performance. Scikit-learn provides accessible tools that simplify this process, making it feasible even for those new to machine learning. Remember, continuous learning and adaptation are key as new techniques and tools emerge. By applying the knowledge gained today, you can significantly improve your machine learning models and contribute to advancements in your field.